Hey, good morning, class. Okay, so for today's class, I just want to do a summary on the course that we have learned this semester. And before I begin, I would like to confirm, yeah, I have not received, or I shouldn't say I haven't received, as for your assignment, yeah, because I straight away mark in Google Classroom, and I will be able to return your mark back to you by Google Classroom, and also you'll be able to see my comment on your assignment report. So if you were to submit your assignment through Google Classroom, then when I return it, when I finish marking all and I return, and then you should be able to see your marks as well as my comment. So even though your assignment is actually a group assignment, where you actually two-person submit one report, but the other person can still submit the same report, then I will mark accordingly, and then feedback your mark and the comment on your part of contribution. But if only one member submitted, then I will only return the mark of that member and comment on his work only. All right, so you will not be able to know your assignment mark if you did not submit. Yeah. So I actually made an announcement in Google Classroom last week. All right, but I still have 7 students who haven't actually submitted themselves. So if you have not submitted yourself, that means I won't be able to return your assignment back to you with the mark. Yeah. And I'm actually in the process of marking. Still have a bit more to go. I hope to finish it by this before the end of the week. And I have also returned some of the work. All right, return work to some students because their assignment report is not satisfactory. All right, so that means you are going to get a mark that is lower than passing mark. Yeah, and this is especially important for those who did not pass your midterm test. So if you did not pass your midterm test and you receive a personal message with the return of your assignment work by Google Classroom, and I actually ask you to submit over the weekend. So if you've done so, then I will mark again, and again your mark will be kept. Yeah, you won't. You'll be kept to amount. You won't actually receive the maximum mark that you will get. This is just to save the trouble of having to do make good. All right, so if you did not submit, resubmit, or your resubmission is still not satisfactory, then I will inform you to sit for a make good test by the end of the week. All right, so be prepared and check your Google Classroom message every day for those who are in question. All right, did you get that? Okay, and I also have some students who have not responded to my comment. Okay, so you are in charge of, you're responsible for your own grade, yeah? So I have already given you a second chance. So if you did not respond within a week, then I will mark accordingly. Within these 2 days, I don't submit too late because I have to finalize your mark by Wednesday. All right, so if you did not submit by Wednesday, then I'll take whatever you have submitted as your final work. Okay, all right, let's start with the revision or summary on what we have learned this semester. Um, Let me share my screen. Okay, so as far as this course is concerned, there are a few main topics. So we started with some overview into the communication system, all right, and some revision or refreshment on the signal analysis. Then the main content of the course basically start with the amplitude modulation. Okay, so this course basically has two portions. One is the analog communication system. The other one is the digital communication system. All right, so amplitude modulation belong to the analog communication system. So as far as the amplitude modulation is concerned, all right, we actually change the amplitude of the carrier according to the amplitude of the message signal. Yeah. So in this amplitude modulation techniques, we have studied four of them. The first one is the double sideband suppressed carrier. Second one is a double sideband full carrier. And third one is single sideband. And the last one is the vestigial sideband. All right. And then for modulation technique, the double sideband suppressed carrier, basically you just multiply the message, the analog message with the carrier signal. Yeah. But for double sideband full carrier, we multiply and we add. Okay. Basically the addition is we add the carrier. All right. We can also produce a double sideband full carrier signal by performing addition first, meaning provide a DC offset to the message first before we multiply with the carrier. So both methods can be used. And then for single sideband, basically is the double sideband suppressed carrier signal pass through a band pass filter. All right. So instead of having double sideband, we just need to transmit one sideband. Yeah. Basically, because both sideband carry the same information. And then for vestigial sideband, the again the modulation technique is similar to single sideband. Again, we take the double sideband suppressed carrier signal and then we pass it through a band pass filter. But in the vestigial sideband, the band pass filter has a wider bandwidth that allow extra about 25% of the single sideband signal to pass through. So basically, this is a more relaxed version of a single sideband. So if you look at the frequency spectrum, double sideband suppressed carrier spectrum has oh, okay. The double sideband suppressed carrier signal spectrum has two sideband. Yeah, one is the lower sideband, and the other one is the upper sideband. Yeah, so both sideband actually carry the same information, and it actually center at the carrier frequency. All right, maybe I should enlarge a bit. Okay, and then for double sideband suppressed carrier signal, double sideband full carrier signal. Okay, the term full carrier meaning a carrier signal is present in the modulated message, the modulated signal. All right, so therefore the spectrum will have a carrier component here at the carrier frequency. Okay, same thing. This is the lower sideband and this is the upper sideband. Um, Then for single sideband, so as the name suggests, the modulated signal only has one sideband. So we can either transmit the upper sideband alone or the lower sideband alone. Yeah. And then for vestigial sideband, the bandwidth is slightly wider, so you can expect to see the spectrum which actually stand beyond the single sideband. So as far as a recovery method is concerned, or the modulation technique, the double sideband suppressed carrier can only be recovered using synchronous detection. All right, or sometimes we call it coherent detection. Yeah. So in the coherent detection method, we actually need to have a local carrier at the receiver. And this carrier signal need to be in synchronization with the carrier at the transmitter. Yeah. And for this kind of detection method, all right, it's actually difficult to have a local carrier that is in perfect synchronization with the carrier signal that is carrying the message into the receiver. Okay, basically what we have here is what we receive, there will be some phase shift, there will be some delay. So definitely you won't be in perfect synchronization. All right. And this actually gives rise to phase error that will actually reduce the amplitude of the recovered signal. So to solve this problem, we actually introduced the double sideband full carrier signal. So double sideband full carrier signal is with the addition of a carrier component. So therefore, in the receiver, we no longer need a local carrier. All right. Uh, in other words, we don't need coherent detection. Even though if you want to, you can still recover the signal using coherent detection. But the benefit of transmitting the signal using double sideband full carrier is that we can use the non-coherent detection technique at the receiver. All right. So there are two types of non-coherent detection method that we have discussed. The first one is the envelope detection, and the second one is the rectifier method. Okay, so both methods do not need a carrier at the receiver. Um, However, for single sideband and vestigial sideband, both types of signal need coherent detection at the receiver. All right. So basically, this is because it's just a um, duration of the double sideband suppressed carrier. So no carrier was sent. So therefore, we definitely need a coherent detection at the um, receiver side. As far as bandwidth is concerned, double sideband suppressed carrier has a bandwidth of 2B. What is B? B is the bandwidth. All right, so this is our B. So double sideband, so that means the bandwidth will be 2B because we transmit two sidebands. Similarly, for double sideband full carrier, the bandwidth is also 2B. Single sideband bandwidth is B only because we only transmit one sideband. Whereas for vestigial sideband, because the bandpass filter allow an extra 25% of the signal bandwidth to pass through and get transmitted. Therefore, the bandwidth of a vestigial sideband is about 1.25 times B. Okay, and then as far as power efficiency is concerned, double sideband compressed carrier, the power efficiency is 100% because all the signal that is used to transmit the modulated signal is all the power. Okay, all the power used to transmit the modulated signal is in the two sidebands, and both of them carry message. All right. Um, Whereas for double sideband full carrier, we have seen that the efficiency is maximum only about 33.3%. Okay, that is because most of the power used to transmit the signal is actually used to transmit the carrier signal itself. All right, and then we have a limitation in this case. The modulation index cannot be more than 1. All right, so therefore that limit our power efficiency to a maximum of 33% only. Whereas for single sideband and vestigial sideband, the both method has the 100% power efficiency. Again, just because all the power is used to transmit the signal, the message itself. All right. Then why you might want to ask, since the power efficiency is so low, why do you still want to use the double sideband full carrier? Okay, so the main reason for using double sideband full carrier is for us to use non-coherent detection method at the receiver. All right, so that is the main reason for using double sideband full carrier. And this kind of recovery method actually will be better than the coherent detection. Yeah, as we known previously, coherent detection will not guarantee that the message can be recovered fully because of phase difference between the local carrier signal and the incoming signals carrier. So no coherent method basically avoid that problem. But again, we pay the price with low power efficiency here. Okay, and then okay, as far as amplitude modulation is concerned, all modulation technique has low noise immunity. Okay, that's because we transmit the signal by changing the amplitude of the carrier. Okay, and most noise are actually amplitude based. So those noise will actually change the amplitude of the modulated signal, and therefore the originality of the message will be changed by the noise. Yeah. And then as far as the standard transmission frequency for AM, the standard is 535 kilohertz to 1600 kilohertz. And then the bandwidth shouldn't be more than 10 kilohertz. All right, so these are the standard that you should be aware of. Okay, and then at the end of this chapter, we actually look at how, no, this is not TDM, this is FDM. So how we actually can perform, we can multiplex various, um, we can actually multiplex various modulated signal so that we can transmit more than one AM signal over the same channel. All right. So the frequency division multiplexing part is where we actually more than one. We combine more than one AM signal so that we transmit over the same channel. Okay. Any question on AM before I move on to the FM?
No question. Move on.
Okay, good. Sounds so tired. Who's that talking? All right. So for FM, we actually study two types of FM. What is FM? FM stands for frequency modulation. So in this modulation techniques, we actually change the frequency of the carrier signal. Okay, the frequency of the carrier signal is changed according to the amplitude of the message. Yeah. Um, So basically, there are two types of FM that we study in this chapter. One is the narrowband FM. The other one is the wideband FM. All right. And then by definition, narrowband FM has modulation index, which is much smaller than one, whereas wideband FM is modulation index is a lot bigger than one. Yeah. And then for the frequency deviation, narrowband FM, the deviation is normally less than 5 kilohertz, whereas for wideband FM, the frequency deviation can go up to as high as 75 kilohertz. And then for the modulating signal frequency, narrowband FM is used to modulate low frequency signal, okay, to be bounded to be less than 3 kilohertz. Whereas for wideband FM is used to transmit the modulating signal of a much higher frequency. Yeah, so you can use it to transmit anything from as low as 30 hertz to again maximum 15 kilohertz. Okay, so as far as the spectrum is concerned, the narrowband FM spectrum is very similar to the double sideband full carrier signal spectrum. We have actually proved that in our class lecture. So as far as spectrum is concerned, narrowband FM spectrum only consists of two sideband. Yeah, whereas the wideband FM spectrum has many sidebands. Okay, theoretically the sideband can go up to infinity. All right. So as far as bandwidth is concerned, the bandwidth of a narrowband FM is about 2B. All right. Whereas the bandwidth of a wideband FM it can go up to infinity, but normally is limited to less than 30 times the baseband bandwidth. Okay. Okay, and then application. See, narrowband FM is normally used to transmit speech because of the limitation on the um, frequency deviation as well as the modulating signal frequency. Yeah, so this is only suitable for speech. Whereas for wideband FM, because the range of the modulating frequency is bigger, and therefore we can use it to transmit speech as well as good quality music. Yeah. Um, And as far as the bandwidth of FM signal is concerned, right, narrowband FM, no question, is straight away 2 times the baseband signal bandwidth. But for wideband FM, it can be any value. Okay. So how do we know the bandwidth of wideband FM signal? So we need to know the bandwidth by looking at the modulation index. Okay, so the modulation index of the FM modulator will determine the bandwidth of the signal generated. So how do we know what is the bandwidth? So there are two ways that we can determine the bandwidth of a wideband FM signal. One is by using Bessel function table. The other one is using Coulson's rule. All right, so both method require us to know what is the modulation index. By the way, what is the equation for modulation index? Delta F over F max, isn't it? Yeah. Again, that's one way of getting your modulation index. The other way of getting the, is there another way? No, that's the only formula. Yeah. But then for delta F basically we can get it by looking at the signal itself. Yeah, so you have to perform differentiation if necessary in order to get the delta F of your FM signal. Okay, and then for power. All right, so as far as power is concerned, the power of a FM signal actually is the same as the power of the carrier. All right. And then the power of the carrier basically is equals to what? Vc square over 2, isn't it? Because the amplitude of a FM signal is constant. All right. The amplitude of a FM signal is constant, is Vc. So the power of the FM signal is actually Vc square over 2. And this power is actually distributed over all the sideband signal. All right. The carrier P naught normally is the carrier power, and P1, P2, P3, and so on are the sideband power. All right, and we normally we use power ratio to compute the power, which is easier. All right, so instead of computing the power of individual sideband, we can straight away calculate the power of the carrier signal, because they will give us the total power, and then we multiply with the power ratio in order to get the exact power that is being transmitted if we were to limit our transmission bandwidth. All right. So the power ratio basically is the square of all the sideband coefficient. All right, so they are called J. So J naught basically is the Bessel coefficient for the carrier component. J1 is the Bessel coefficient for the first sideband component. J2 is the second sideband, and so on, all the way up to N. Okay, and so if we use bandpass filter to limit the transmission bandwidth, then therefore some of the sidebands will not be transmitted. Therefore, the power of the actual FM signal being transmitted will be reduced, right? And therefore, to actually compute the power after the bandpass filter, we can make use of the power ratio. Yeah, using the same um, coefficients, uh, except those sidebands that has been blocked by the bandpass filter. Okay, we have done some exercises during lecture as well as tutorial. Okay, so you may want to go through it in details if you want to. And as far as FM signals are concerned, there are various standards, but the common one is the commercial radio standard, commercial broadcasting standard, and this is 88 megahertz to 108 megahertz. Okay, what it means is this is the carrier frequency. Yeah, the carrier frequency of the FM signal is between this range. And then as far as bandwidth, is limited to 200 kilohertz. Yeah, and the frequency deviation is limited to 75 kilohertz. Okay, so that means if your signal, the FM signal, you have to make sure it's always less than these two values. Okay, of course, if you want to get the work until the max you can, but normally it's not advisable because you need to have a guide band between individual station or between two stations. Okay, and as far as for generation of FM signal is concerned, there are two ways. One way is the direct, the other way is indirect. So for direct method, we can make use of the double sideband suppressed carrier method. All right, and that will give us the narrowband FM signal. And you can also make use of the VCO, the voltage control oscillator, to generate the narrowband FM signal. Okay, and this is only suitable for narrowband FM. So for wideband FM, these two methods are not really suitable. For wideband FM, normally we use indirect method. Okay, so indirect method basically make use of frequency multiplier. All right. So what we have studied is the Armstrong method. Yeah. So in the Armstrong method, we actually um, produce a narrowband FM signal first. Yeah, using the message signal that we want to transmit, we pass it through a narrowband FM signal generator. So it can be this or this. So this will produce a narrowband FM signal. And after that, we pass this signal through the frequency multiplier block. All right. So we actually make use of two-stage multiplication according to Armstrong method. So we have a stage one multiplication that is a factor of n1, and we have a second stage of multiplication here at the end, which is n2. All right. And then a lot of times, the carrier signal, the FM carrier signal to be transmitted, the multiplication factor is different from the frequency deviation. All right. The frequency multiplication method basically will multiply the carrier signal as well as the frequency deviation by n times. Yeah. But a lot of times we find that the ultimate carrier frequency of the transmitted signal, the multiplication factor is not the same as the multiplication of the frequency deviation here. All right. Therefore, we use a mixer here to shift, okay, to shift the carrier frequency. Yeah. So again, by the mixer will actually multiply the FM signal first with the local carrier, okay, with the frequency FLO. And here the output of the mixer will produce again two sets of signal with different frequencies. So this band pass filter is actually used to choose, right? It's used to choose the frequency component that we want, all right? And how do we know which one we want? The one that we select has to be be of a frequency after we multiply by n2 will give us what we need at the end here. Okay, so the carrier, the frequency that we are going to transmit, as well as at the same time is going to fulfill the frequency deviation that we need to transmit over here. So again, for this, we have gone through, I think, one example in lecture, and we also done two exercises in the tutorial. Yeah, so for details, you may want to refer. Okay, and then for recovery, we actually quickly look at the 2D recovery method. So the first recovery method is by making use of the discriminator circuit, and that's for direct, and for indirect, we actually make use of a phase lock loop. So yeah, as compared to AM, all right, we have studied two analog modulation techniques. So let's do a comparison, and we actually did it at the end of this chapter. So as compared to AM, FM has better noise immunity. All right, that is mainly because the message, the amplitude of the message signal is now carried by the frequency of the carrier signal instead of the amplitude as in AM. And the FM signal actually only require a shorter antenna in order to receive and transmit. That is because we actually transmit FM at a much higher frequency as compared to AM. All right. So we know that the length of antenna basically is proportional to the wavelength of the signal, right? So a high frequency signal basically means a shorter wavelength. So therefore we can use a shorter antenna for FM as compared to AM. And then FM has also used the power more efficiently as compared to AM. And basically this is in compare with the double sideband full carrier in AM. All right. So if we choose the modulation index correctly, then we should be able to make most efficient use of the power. Then for FM signal normally has very wide bandwidth, okay, because we want to transmit signal of wider frequency range. So therefore the FM, and then the FM signal also has many sidebands as far as wideband FM is concerned. So normally it has many sideband, and the bandwidth is normally wider, and and it's actually a lot of times wider than AM, right? The AM bandwidth is only about what, 10 kilohertz, right? Yeah, but then for FM, you can go to anywhere near to 200 kilohertz. Yeah, so this is actually 20 times more than the AM bandwidth. However, the FM circuits are actually more complex as compared to AM. All right. For AM, we've seen that to generate AM signal, you just need an adder and a multiplier, and then at the receiver, what you need is just, if you are using coherent, it's just an amplifier followed by a low pass filter. All right. And you are using non-coherent detector, then basically you only need what, diode, some resistor and capacitor. Yeah. Whereas for FM, we can see that the generation is a lot more complex. Yeah. So unless you're talking about narrowband FM, but most of the time FM is useful because of the in the wideband FM. All right. So you can see that to generate it, definitely we need to use frequency multiplier, and we need a narrowband FM generator with this entire circuit. So therefore the generation, as far as generation is concerned, the circuit is more complex, and for recovery also is more complex, yeah, as compared to AM. Okay, so that is a brief summary on FM. Can you follow?
Yes.
So let me move on to the next chapter that we study in this course, and that is on the pulse modulation. Pulse modulation was a very short chapter. Basically, this is the link from analog communication into digital communication. All right. So in pulse modulation, we actually studied that we actually need to sample the signal. Okay, given an analog signal, we need to sample it, and the sample of the signal gives us the pulse. All right, pulse that represent the message signal itself. So in this chapter, we studied that the sampling frequency, okay, must follow the Nyquist theorem. So the sampling frequency must be at least twice the highest frequency in the message signal that we want to transmit. Yeah. And in this chapter, we study three types of pulse modulation techniques. First one is the pulse amplitude modulation, or PAM in short. So in pulse amplitude modulation, the the amplitude of the pulse is made proportional to the amplitude of the message signal. Okay. And whereas for pulse width modulation, the width of the pulse or the pulse duration is proportional to the amplitude of the message signal. And for PPM, the pulse position modulation. And in this modulation technique, the pulse is delayed, and the delay time is actually proportional to the amplitude of the message signal. Okay, but the important modulation technique in this chapter is actually the PAM. Okay, because this PAM is going to lead us to the next chapter. So quite a lot of time has been spent on studying the PAM. So in short, basically the PAM signal can be generated by using the sample and hold circuit. Okay, that is what is normally done in practice. And recovery also is done using sample and hold techniques, and then followed by a low pass filter to recover the message signal itself. Okay, and at the end of this chapter, we also look at the how we can time multiplex more than one PAM signal for us to transmit over a single channel. Yeah. Then very short. This chapter actually is very short. But the next chapter, okay, which is a more important chapter, is the baseband digital communication. Right. So in the baseband digital communication chapter, basically what we study mainly are these few processing block, signal processing block. All right. We have an analog message signal that we want to transmit using baseband digital communication technique. So what we need to do is the first thing we need to convert the analog signal into digital first. Okay, so this is done in the ADC block, analog to digital converter block. Then in this block, so basically the method we study is the PCM. PCM stands for pulse code modulation. So in this pulse code modulation technique, we first sample the analog signal. Okay, this is the same as the PAM sampling that we studied in the previous chapter. And after that, we quantize the sample signal. All right, then after that, we encode the quantized sample. Right, and after the signal has been encoded, all right, so we actually pass the signal through a line coding block. So line coding block, basically we choose a suitable line code to represent the encode sample. All right, and after that, the line code what is line code? Line code basically is the electrical waveform that we want to use to represent the encoded sample over here. Okay, so the electrical waveform is then passed through a filter, and we call it a pulse shaping filter. All right, so this pulse shaping filter basically will actually, as the name suggests, it will shape the pulse that we want to transmit. Okay, the line code here basically is the produce electrical waveform that is ideal. Okay, and it normally has very wide bandwidth. Okay, not suitable to be transmitted over the wired channel. Baseband means we actually transmitted over wired channel. Okay, we cannot transmit a digital signal uh, how to call it, wirelessly. Okay, so so we basically pass the signal through a pulse shaping filter to limit the bandwidth required. Yeah, and normally because wired channel has limited bandwidth lah, as compared to wireless channel. Wireless channel normally has a very wide and uh, unlimited bandwidth. All right, but again, you talk about wireless channel, you still need to limit your bandwidth because you want to allow other signal to be transmitted as well. So for baseband, the PCM, as far as PCM technique is concerned, all right, so for sampling, again, we have to make sure that we sample our signal at least 2 times the highest frequency in the signal, the baseband signal itself, or the analog signal itself, right? And then as far as quantization is concerned, quantization process is to make sure that the voltage level of the sample produced uh, is limited to some discrete value only. All right, we cannot have continuous amplitude. We can only have, as far as digital information is concerned, the amplitude has to be discrete. All right, the sampled signal basically is discrete in time already. Yeah, remember what is analog signal? Analog signal is a signal has is continuous in time, also continuous in amplitude, right? But for digital signal are discrete in time as well as discrete in amplitude. So the sampling process basically produce a discrete time signal, and the quantization process will produce a discrete amplitude signal. Okay, so basically we limit the amplitude to L levels. Okay, so we have a L number of amplitudes. So how do we decide our L? Is by determining how many bits we want for our binary signal later on, or the digital signal later on. Yeah. So n bits normally will give us the L level, yeah, by using this equation. And then the delta V, which is the quantization interval, is 2 Vp over L. So 2 Vp basically is the peak to peak voltage over how many levels that we actually use. Then the error, as far as a quantization error is concerned, is delta V over 2. All right. So this equation only apply for uniform quantization. All right. If we are talking about non-uniform quantization, we actually look at two laws that we can use to perform non-uniform quantization. Basically, non-uniform quantization will require the compending process, meaning we compress the signal at the transmitter before we perform uniform quantization, and then at the receiver we expand the signal. Okay, so if you were to do compending process, then there are two laws that we can follow. One is for mu law, the other one is A law. Right, we actually had a brief discussion on this. Okay, and encode. Okay, as I mentioned previously, the encoding process basically is to convert the quantized sample into binary code words. Okay, then the signal to quantization noise ratio can be calculated by using this equation as far as uniform quantization is concerned, right? It's 6.02n plus 1.76. Yeah, and in this chapter also we learn how to calculate the bit rate. Okay, bit rate is given by the product of n and fs. Okay, where n is the number of bits we use to represent each sample, and fs is our sampling rate. Okay, and minimum bandwidth for baseband digital communication. The theoretical minimum bandwidth is RB over 2. All right. Again, it actually depends on the line code you use. Yeah. So if you use, okay, let's talk about line code. Okay, as far as line coding is concerned, line coding is used to convert the binary information into electrical waveform. Okay, so there are two main category of line codes. One is a non-return to zero. The other one is return to zero. Okay, non-return zero is what we call full wave, and then return to zero. Basically, what we learned was half wave. Okay, so this is a full wave pulse. This is a half wave pulse. Okay, and then there are four types of line coding techniques that we have learned. One is the first one is the OOK. OOK stands for on-off keying. And then we look at polar. We also look at bipolar and also Manchester code. All right. So with so many line coding techniques to use to be chosen from, okay, how do you choose the suitable line code? Okay, depend on your application. All right. So of course, these are some of the properties that we desired for a good line code. Okay, first one is of course the bandwidth need to be small. Okay, and the power usage need to be efficient. Okay, and of course zero DC. The other one is bit synchronization capability. So meaning we can actually at the receiver side, we can actually recover the clock signal and then we can perform the sample and hold. Okay. Then of course, high noise immunity. All right. The last one is a good line code. Ideally, if possible, you want to have an error detection and correction capability as well. All right. So this is the ideal list. Okay. In practice, you have to trade off between these properties. Okay. There isn't a line code that actually fulfill all the. Do we have one? No, we don't have a line code that fulfill all the desired properties here. All right. So depending on which one, which property is more important to you, so you may choose the line code accordingly. Okay, and then the last topic of this chapter is the pulse shaping. Right. So as far as pulse shaping is concerned, pulse shaping basically is to uh, ensure zero ISI. Okay, ISI stands for intersymbol interference, and also improve bandwidth efficiency. Okay, so for bandwidth efficiency, of course, ideally we want to have as low and small bandwidth as possible. But we also know that if we want our bandwidth to be small, then we have to use a sync pulse where R is equals to zero. However, sync pulse is difficult to generate in practice. Yeah, so we actually can use a raised cosine pulse. And again, when we use a full raised cosine pulse where R is equal to 1, that means we are going to increase the bandwidth. Yeah, so the bandwidth efficiency will be lower. And if you use a raised cosine pulse as compared to a sync pulse. Okay, so that is for chapter, I think all we learn in this baseband communication, right? Yeah, so you can see in order to transmit analog signal digitally, we actually have to go through quite a number of processing steps, right? Before we transmit it. So you may think, oh, why so much hassle? Just transmit as it is, correct or not? But in fact, we did it for some benefits that we're going to get. So basically, if you transmit an analog message digitally, that will actually increase the noise immunity of the signal, right? So when we transmit the signal digitally, basically, as far as the receiver is concerned, a digital message has only two amplitude. One is high, one is low. So it's easier to recover. All right. And then for digital communication technique, we are able to repeat the signal, okay, along the transmission path. Repeat the signal meaning when the signal come, we can actually work out, we transmit the signal from here. Okay, along the transmission path, we can actually build repeater. Okay, we can build many repeater before you actually reach the destination. So the function of a repeater basically is to sample the signal, clean up the signal and transmit it again. So basically, whatever signal that come out from the repeater, it will be the same as the signal that you send from this transmitter over here. So they will ensure the received signal at the other end uh, will be low noise, okay, low distortion, and so on. So that it can be recovered as well. Yeah. So and then as far as the digital signal representation is concerned, is uniform. Okay, so regardless of what kind of analog signal that we are going to transmit, we can actually represent them using just a series of ones and zeros. So it's very easy to represent. And also storage and processing. So it's actually easier to store and process digital signal, right? Just the same processing block for all digital signal and storage as well, right? And then flexible. Flexible is as far as digital communication is concerned. Whenever you want to, um, how to put it, flexibility. Flexibility means you can easily construct a digital communication system using the available digital processing block. All right. So it's not like analog. Analog, you have to actually design and then match it with the signal that you want to transmit. But for digital, everything is in one and zero. All right. So you can make use of any available processing block to do it. However, the digital communication techniques end up with a much larger bandwidth. All right, much larger bandwidth. As we have seen previously, the bandwidth basically will be here, baseband. Where is it? Okay, the bandwidth is and the bit rate is NFS. Okay, and then the bandwidth is RB over 2. So that means the minimum bandwidth required will be NFS over 2. All right. So for analog transmission, basically you just need what the Fmax, isn't it? Fx, Fmax only, or 2 times Fmax. But for digital transmission, you need to multiply with n, and this Fs is 2 Fmax, right? So okay, let's say you use Fs being equals to 2 Fx, but we have a factor of n, and the minimum bandwidth n over 2 lah. All right. So that means if you will use n equals to 8, then your bandwidth is 4 times. All right. If you use n equals to 16, then your minimum bandwidth requirement is 8 times. All right. So as far as digital signal transmission is concerned, the bandwidth normally is a lot larger. Okay. Okay. So again, you need if your signal is analog in nature, then definitely you need the analog to digital converter block. And so this system is not compatible with analog system. Yeah, and of course for digital communication, because we do a lot of sample and hold, a lot of sampling process. So therefore, we need good synchronization between the processing blocks. Okay, so that is for baseband digital communication. Any question on this? So I just want to give you an overview on what we have learned in this course. All right, as far as the detail, the calculation, the design, and so on, you can refer to tutorial. I don't think I have time to go through all those in details. Yeah. Okay. So let's take a break before we review the last 2 chapters. Okay. Anybody listening? Okay, only Yao-Ting respond. All right, so let's take a break and then we resume. Yeah, Sharon. Let's now it's 12:01. Let's resume at 12:10. You look at my comment. If my comment say resubmit, then you resubmit. If my comment do not say resubmit, then no need to resubmit. Function no need, no need to resubmit. I didn't ask you to resubmit. Okay, are we all back? Okay, it's good. Let's continue our discussion. Okay, so the last two chapters are mainly on digital modulation techniques. Okay, so what is digital modulation? So in digital modulation, we actually use analog carrier to convey digital information. Okay, and this is for RF communication. So it means RF means wireless. All right. So as I mentioned previously, we cannot transmit 1 and 0 or the line code rectangular pulses over a wireless medium. Okay. So if we want to transmit our signal over wireless medium, we definitely have to use an analog carrier. Yeah. So we have studied three main types, or in fact, there are four types of digital modulation techniques. So the first one we studied was ASK. We started with the simple one, two ASK, and then followed by two PSK, then two FSK, and we also have a brief look at QAM. Okay, so as far as ASK is concerned, ASK means what? ASK stands for amplitude shift keying. All right, so amplitude shift keying. So what it means is the amplitude of the carrier represent the binary data. All right, so what we did is we transmit a binary one with a carrier of let's say carrier signal amplitude A, and then we send binary 0 with the carrier amplitude 0. So that means no carrier at all. All right. So in a way, 2ASK is very similar to OOK, the on-off keying method. So when to transmit a binary one, we on the pulse. Okay, we on the sine or cosine signal. And then to transmit a binary 0, we off the cosine signal. Okay, the bandwidth for 2ASK basically is the same as the AM signal. So it's 2B, where B is the baseband signal bandwidth. Okay, and to generate ASK signal is very similar to double sideband suppressed carrier. All right, and we normally use on-off keying input. So meaning our pulses are either positive uh, pulse. The input binary signal normally has a positive pulse for 1 and 0 for binary 0. Okay. So again, we make use of a multiplication technique. We just multiply the digital data with carrier signal. So for recovery, we can actually use coherent or non-coherent method. And then the method used is very similar to amplitude modulation. Okay, basically ASK is just a digital, the signal we transmit is a digital instead of analog in AM. Okay, and then for PSK, we actually look at two PSK. PSK P stands for phase, yeah, phase. So PSK is for phase shift keying. So here we transmit the digital data using a carrier signal with a different phase angle. All right. For example, we transmit a binary one with a 0 degree phase angle, phase shift, and then transmit a binary 0 with a 180-degree phase shift. So the bandwidth of this signal again is 2B. Okay, and then how to generate this 2 PSK signal is very similar to double sideband suppressed carrier again. Okay, where we multiply the digital data with a carrier signal. But the difference between PSK and ASK is that the digital data need to be polar. All right, it need to have a positive amplitude for binary 1 and a negative amplitude for binary 0. Yeah. So that will ensure that the modulated signal has 180-degree phase shift. And then for PSK, only coherent detection is possible. Okay, and then how to recover it is very similar to double sideband suppressed carrier lah. Then we study the 2FSK. We started study all the binary SK lah, yeah. So the next one we study was 2FSK. So in 2FSK, we actually use a different frequency to transmit the binary 1 and binary 0s. Yeah. So because we use two different frequencies to transmit the binary data, and we need to have some separation between the two frequency that we use. Therefore, the bandwidth of FSK signal is wider than the bandwidth for PSK and ASK. Okay. So again, we require the minimum 2B plus 2 delta F. Delta F is the frequency separation. So basically, it's the 2 delta F is the separation between the two signal frequencies that we use to transmit binary 1 and binary 0. So to generate the FSK signal, there are a few ways. Yeah. So one of them is the VCO, which is same as the FM signal generation. And we can also use two ASK using two carrier frequencies. And for recovery of FSK signal, there are two ways. One is a coherent, the other one is a non-coherent. All right, so for details, you may want to refer to the lecture notes. And then the last one that we study was QAM. So QAM basically, we change the amplitude as well as the phase angle of the carrier signal to represent the binary data. Yeah. So QAM is normally used for higher M level. Yeah, higher M level, where we need a lower bandwidth as well as we need a small phase angle between the signal. No, not small phase angle, bigger phase angle between the signal. Because if the phase angle is too small, when you increase your M level for PSK, the phase difference between two signal will be too small. Then it might pose a difficulty on your hardware design to recover the phase angle of the received signal. And then, okay, a brief discussion on these three types of modulation technique. ASK is very easy, very simple to generate. Circuit also very simple. But then it actually has the same problem with AM, where the signal is actually susceptible to noise. All right. So therefore, ASK is only used on low noise channel. All right. For PSK compared to ASK is less susceptible to noise. Yeah, basically because the information on the digital data is actually carried by the phase angle of the carrier, not by the amplitude. PSK has same bandwidth as ASK, okay, and the bandwidth is lower than FSK. Yeah, of course, the bandwidth of a PSK is 2 PSK is 2B, right? Yeah, and bandwidth of 2 FSK is 2B plus 2 delta F. So from here, you can straight away see that the bandwidth of the 2 PSK signal is less than the FSK signal. However, PSK has this restriction. We must use coherent detection technique. All right, except for differential PSK. Yeah, if you use differential PSK, then we don't need coherent detection. And then the application of PSK. PSK modulation techniques are normally used for RFID, Bluetooth, and also the WLAN. And for FSK, FSK again, because we carry the binary information in the form of frequency, so it makes the signal less susceptible to noise as compared to ASK. Yeah, but it has a problem of wide bandwidth requirement. And the application is normally used for high frequency radio transmission. This radio here is not the radio station we're talking about. This radio means is the radio frequency. All right. So that is a short summary on the few digital modulation techniques that we have learned. So at the end of this chapter, we actually look at the definition for baud rate or symbol rate. Okay, baud rate of symbol rate is given by the bit rate divided by n. And what is n? N is the number of bits that represented by each symbol. Okay, so n is log 2m. And then for n that is greater than 1, we can see that your s is less than your bit rate. Your symbol rate is less than the bit rate. Okay, then for the next chapter, we actually look at the performance. We compare the performance of various digital communication or modulation techniques, okay, by actually focusing at three measurement criteria. So the first one is the probability of error, and the second one is the bandwidth efficiency, and the last one is the power efficiency. Okay, and the probability of error we have derived, right, the probability of error for different modulation techniques as follow. So for polar and 2 PSK signal, the probability of error is Q of A over sigma. All right, and then for OOK and 2 ASK, the probability of error is Q of A over 2 sigma. Okay, and then for FSK, the probability of error is given by Q of A over root 2 sigma. All right, so Q stands for Q function. So to find the probability of error for various modulation techniques, you need to make use of the Q function table. Right? If you know the amplitude of the signal and you also know the power, the noise. Okay. Then looking at the bandwidth efficiency. Bandwidth efficiency by definition is the ratio of bit rate over bandwidth use. Okay, over bandwidth required. So for MPSK, the equation for bandwidth efficiency is log 2m over 1 plus r. All right. So we can see that from this equation, if you were to increase our m level, basically it will increase our efficiency. Yeah. But for MFSK, okay, the equation for non-coherent and coherent detection is given here. So again, depending on what recovery method you're going to use at the receiver, if you're going to use coherent method, then this will be the equation for the bandwidth efficiency, and the non-coherent will be this one. But generally, we can see that if you were to increase our M level, that means we are going to need a higher bandwidth. All right. So therefore, the bandwidth efficiency will drop. Yeah. So as far as MPSK and MFSK are concerned, the MPSK gives us better bandwidth efficiency. All right. The last criteria that we compare was the power efficiency. All right. So in power efficiency, we have actually looked at, in order to compare the power more fairly, we actually look at the power required to maintain the probability of error. Yeah, so we can actually see that in order to if we want to maintain the probability of error, when we increase the M level, we will find that we actually need more power to maintain. So therefore, the power efficiency of the MPSK will drop when we increase M. All right. However, for MFSK is that when we increase M, we actually need lower power in order to maintain the probability of error. So that gives us a better power efficiency. Yeah. So as far as the application is concerned, which modulation technique to use, again, it depends on what you want to use it for. All right, and also depend on you want to is bandwidth a problem? Okay, is bandwidth a limitation or is power a limitation? Right. So basically, by reading your assignment report, I think most of you already has mastered it, yeah. When to choose, what techniques to choose, based on your evaluation, yeah. Whether you want bandwidth or you want power. Is power a problem or is bandwidth a problem? Okay, so your assignment basically is to assess, right, whether you are able to make a decision, okay, using some conflicting requirement. Yeah, conflicting requirement means, if I choose this, I have problem with my bandwidth. If I choose the other one, I have problem with my power. So which one should I choose? Yeah. So I think most of you have done the selection right. So therefore, I think most of you got no problem lah, as far as this part of the course is concerned. Okay, so that ends my discussion on the summary of the course. Do you have any questions? Okay. For your final exam, okay, first thing about your final coursework mark. Your final coursework mark will be the sum of your midterm test mark and the sum and the assignment mark. All right, you know your midterm test mark already, right? So after I finish marking all the assignment report, I will return all your assignment to you with the mark. All right. So from there, you can actually compute it yourself. Okay. So your midterm test mark is based on upon 50%, right? Your assignment mark will be upon 100%. So your final coursework mark will be your test mark plus your assignment mark divided by 2, or divide your assignment mark by 2 plus your coursework mark plus your test mark, then you get your final coursework mark. Okay. And then for your final exam, okay, so this is 40/60, right, this course. So your final exam, I'm going to conduct your final exam in a different classroom, yeah, because this classroom is very full, full of a lot of information. So I'm going to give you the class code next week, and then I will invite you to join so the new classroom to conduct our exam on. So please accept the invitation, check your email and accept the invitation, then you'll be allowed into the classroom where we conduct your final exam. And another note on your final exam is that you're going to submit using Google Form. All right, you're going to submit using Google Form. I think I mentioned this, right, in the last lecture. You're going to submit using Google Form because this is to make sure you only submit one time. All right, for your test and assignment, you can submit many times. But then if your exam, I will have problem, Even your test also, some of you will have problem identifying which one is the latest one, So for final exam, to avoid all this conflicting information, I only limit your submission to one time only. All right. So, and I will do that using Google Form. All right. So that is for your final. So, and then there will be your final. I actually will divide it into 2 stages. All right. So again, for final exam, I only set 2 long questions. So one long question is on analog communication system, and the second long question is on digital communication system. Right? And then you are given 1 hour and 15 minutes to answer each question. So I will release the question in 2 stages. All right, first stage, I'll release first question, and then you have 1 hour and 15 minutes to answer. All right, and then at the end of the 1 hour and 15 minutes, you stop writing and then you start scanning your solution. Okay, scanning your solution and then save it as a PDF file with your name or your ID number. All right, don't give me the default cam scanner or whatever. Please name your file according to your name and your ID number, and then you submit using the Google form. So only one time submission is allowed. So make sure you capture your solution correctly. Yeah, you capture them correctly, and then save it correctly. Check your file first before you submit. All right, because we are only allowed to submit one time. So if you submit the first one wrong, I don't know how to save you already. Okay, and then 15 you have 15 minutes to do your scanning, naming, as well as submit. So I think that is more than enough time. So if you submit earlier, then you can go for a break. So within this 15 minutes, say include break. And then after that, we come back. Then I'll release second question. So for second question, again, you have 1 hour and 15 minutes to solve. And then after that, same thing lah. After 1 hour and 15 minutes, you stop writing and then you start scanning your solution again. Yeah. So you basically write your answers on the paper lah, on your own paper. Okay. Yeah. Yeah. Okay. And is that clear for your final? You know how to submit using Google Form, right? So I don't have to give you a mock. I was thinking whether I should give you a mock or not. Can then no need mock. I think year 3 you should be quite familiar with it. Okay. So what else I want to say about your final? Oh yeah, another thing on your paper. What is more important is on your paper, make sure on the first piece of the paper used for each question, you write your name. Okay, make sure you have your name, or else when I mark, I will have problem. And then furthermore, if you don't name your, just to save, just in case some of you forgot, so kanchiong forgot to name the file according to your name, then at least you have your name written on the first piece of paper. Then when I mark, I know who that solutions belong to. Okay, that is for double precaution. Okay, what else? Okay, do you have any other issue that you want to raise? No? I think you are more kanchong with your products, right, on Wednesday? All right lah. So if you have any other questions after this, because I may not meet you again, then you can always email to me, yeah.
Miss, this Wednesday no class, right?
No class because you have projects, so no class this Wednesday. And then I think there's one tutorial on Thursday, right? So I was thinking whether you want to have the tutorial class or not. Because I actually looking at what we have done, there's nothing for me to say anymore. Unless you have question that you want to ask. So do you want to have class on Thursday? I think it's one tutorial group I have to meet on Thursday. Not Thursday. Yeah, Thursday. Okay, so just a final reminder, because I actually asked a few students to resubmit their assignment. So I'm going to mark it over these 2 days, and then I'm going to add with your test mark. So if your test mark is below 50%, then I'll call you for make good test. Yeah. So make sure you check your classroom message as well as email. I think most likely I'll email you also. All right, in case you need to sit for make good. And if your resubmission is satisfactory, then most likely no need to sit for make good. Okay. And I noticed a few did not submit themselves, so that means you will not receive your final coursework mark. Yeah. This is who? Konjen Tung and Teo Leong Ho. All right. So Konjen Tung and Teo Leong Ho, you did not submit the assignment yourself. So I'm going to mark your assignment based on what your partner has submitted. All right. But I will not be able to return your coursework mark to you. Yeah. Okay. Jung Tun and Leong Ho, are you listening?
Yeah, miss.
Upload later. Submit now lah. What you want? Later means what? Tomorrow, next week.
No, later
today.
means after 1
Today.
hour, after 1 hour.
Okay. Today okay. Yeah, I can. I saw it. Can say. I saw it just now. Before the beginning of the class, you did not, but now I checked. Yeah, you already done. Okay, so do you have other issue to raise? If not, then we can end the class here. And I wish you the best for your projects as well as your exam. Yeah. Take care. Yeah, you all take care also. Don't jalan-jalan. You need to take good care of your health. So that you can sit for exam. Who go jalan-jalan? There's one student, you want to go jalan-jalan, you go and ask me got class or not. I say, don't jalan-jalan. Aiyo. Yeah lah. This now positive cases is rising, and then you can never know who is out there that is carrying the virus. Okay. All right. Okay, better don't jalan-jalan. Spend more time in your preparation for your exam and do well in your exam, yeah? Yeah lah. Graduate online. Yeah lah, most likely you're going to graduate online. No more convocation also, isn't it? I think the last two conversation has been kind of cancelled already, so no more convo. But your year 3 not yet lah. You got 1 year, so you got chance some more. Yeah, convo is actually has a lot of fun, right? As far as you're concerned, right? Celebrate your achievement. Yeah, I don't know how your convo is going to be like. Anyway, you still got one year to go. Who knows? By that time, maybe you can have your convo. So make sure you do well and pass. Then you can graduate on time. Yeah, lor. I don't know. With the cases or the pandemic going on like that, I don't know when we can go back to campus to have class. Okay. Anyway, but you have enjoyed your 2 year of campus life, right? Not like the fresh one, the year one student, they haven't actually experienced a campus life. Okay lah. All right. So okay, let's end the class here. Okay. Bye bye. You all take care also.
Thank you, Miss. Bye bye.
Bye.